Hi everyone. In this video we're going to talk about the functional group called the amides, A-M-I-D-E-S. I'll also mention you might hear it referred to as an amide. Typically if you come from England or some other former colony of England, most people from those places call it an amide. It's kind of like potato, it doesn't really matter. I tend to pronounce this as an amide. So what exactly is an amide? Well, an amide comes about from the reaction of a carboxylic acid plus an amine. When you mix those together, they'll form the new functional group called amide or amide. Okay, just be careful about not confusing A-M-I-D-E with amine, A-M-I-N-E. These are different. So let's just draw out an example of this. Let's say I took acetic acid and reacted it with methylamine. All right, so what's happening in this reaction, sort of like what we saw when we were discussing esters, is that this nitrogen is going to now react with the carbonyl. So we can draw that this way. This will then go through an intermediate that then is going to spit out the OH group, and that OH will then abstract one of the protons here. So when we mix a carboxylic acid and an amine together, one of the byproducts is now going to be water. The OH and the H will combine as water. And the product will now have a covalent bond between the nitrogen of methylamine and the carbonyl of acetic acid. So the product you get here would look like this. Okay, so we now have formed the new amide bond right here. And the other byproduct is water. So very similar to what we discussed with esters. It's just that instead of using an alcohol to react with carboxylic acid, we're going to now use an amine. I will mention that I haven't really drawn this arrow as a reversible arrow like we did with esters. That's because the product that's formed, the amide, is much more stable. Okay, so the equilibrium of amide formation favors the formation of the amide bond much more favorably than it does, say, in an ester type formation reaction. So we have now an opportunity to look at this in terms of naming an amide. So this nomenclature is sort of similar to esters, but does have some slight variations. So let's name this compound over here, and then I'll go through some of the rules. This would be called N-methyl acetamide. Okay. And that's because I now have a methyl group directly attached to the nitrogen. I list that first. And then I take my corresponding parent acid, which was acetic acid. Okay. And what I'll do is I'll just drop off the IC acid and tack on amide. So this now becomes acetamide. But I list the things attached to the nitrogen first, and I usually will list a capital N for each of the different substituents that might be on there. Now it turns out that amides come also in 3 different flavors. Let's look at this version. Oops, not NH3. You typically don't protonate an amide like that. You would have this versus the one that I just made. And then lastly, I'll look at this amide with 2 methyl groups. Now, sort of like what we talked about with amines, amides can come in several different flavors. This one here, notice there's no extra carbon substituents coming off this one. This is called a primary amide. This nitrogen of the amide has 2 carbon substituents, so this is called the secondary. And then this one would be called a tertiary amide because it has 3 carbons coming off of it. So when you want to name these, we've already named this one. This would be called N-methyl acetamide. That's that one. But how would we name this one? You just call it acetamide. Okay, so there's no carbon substituent coming off of the nitrogen, so we don't have to put anything in front of the name. We've already named this one. This last one would just be called N, N dimethyl acid amide. All right, so that takes care of nomenclature and structure of an amide. In the next section, we'll talk a little bit about physical properties, and then lastly, we'll talk about hydrolysis. One of the things that's very unique about amides is their ability to exhibit what's called resonance. We've talked about resonance in prior lectures, but resonance is basically the sharing of electrons across several bonds. And if I were to draw a resonance arrow or resonance structure of the amide, what I would get would be the following. Remember, the resonance arrow is a double-headed arrow that looks like this, so we'll just call this resonance. So I'm going to sort of spread the electrons across those three atoms. What I would get would be a structure that looks sort of like this. Okay, and so you notice in the resonance structure now the carbon-nitrogen bond is actually a double bond. Now this has some very important ramifications when it comes to the properties of amides. Because of this resonance, this resonance form is actually a fairly significant resonance form for amides. And we often call this a pseudo double bond. It's not a full double bond, but because this resonance structure does play a significant role, it's sort of like a half double bond. So it basically helps to stabilize the N-carbon bond, and so they're not nearly as reactive as, say, an ester might be. Also, what this prevents, because it's a pseudo double bond, it prevents the rotation about this carbon-nitrogen bond. So I cannot simply rotate. I'm going to put a big X through this. I can't do the following very easily. Okay, so the left hand of the molecule I'm going to keep the same. I can't physically twist this methyl group so that it's now sticking down and the hydrogen would be up. I can't do that rotation without inputting a significant amount of either heat or light energy or something like that. So amides do not rotate. So the N-carbon bond does not flip back and forth. So this, as I mentioned, has some significant ramifications for stability. If you were to compare the stability of an amide to, say, an ester, let's look at the half-life of hydrolysis. Okay, an ester okay, if we want to break that ester bond using either acid or base catalyzed hydrolysis, you know, it definitely will work. But let's actually just think about if we put this ester just in pure water, what would be the sort of rate of hydrolysis? Well, a typical ester can survive about 72 hours. Okay, so if you were to measure the hydrolysis of this and measure when it reaches half the amount of hydrolysis, it'd be about 72 hours. However, if you take an amide, similar type amide, okay, and you put this into pure water and let it sit, the half-life of amides is anywhere now between 100 to 1,000 years. We'll just say 100 years. Okay, so amides, as you can see from just this simple demonstration here, amides are much, much more stable than the corresponding esters, and that all goes back to the fact that they have this pseudo double bond character. This is also the reason why nature has chosen the amide bond as the glue or the bond that's going to stick together our amino acids to make proteins. Our proteins contain these amides, which are much, much more stable than an ester would be. All right, in the last section, we're just going to talk finally about the physical properties of amides. All right, in the last section of this video, we're just going to briefly talk about the physical properties of amides. Primary amides, it turns out, tend to have higher melting points, boiling points, and solubility than the corresponding carboxylic acids. Let me just show you an example. If I were to compare butanoic acid versus butanamide, and let's actually just look at their boiling points. Okay, butanoic acid, I think it's about 163, whereas butanamide's quite a bit higher. It's up at 216. Now, one of the reasons for that is, in the prior section, we talked about the sort of ultrapolarity of this bond, the sort of pseudo-double bond resonance character of this. But also, this has the ability to form several more hydrogen bonds. So if we look at the total number of hydrogen bonds that an amide can form, there would be 3 here coming off the electron pairs. But there's also going to be 2 off of the 2 hydrogens. Okay, so this can actually form quite a few hydrogen bonds. This one can also form 5. Okay, so I'd have 1, 2, 3, 4, 5. But notice in the amide, I'm getting 2 hydrogen bond donors there. And I also have the extra added polarity of the resonance. So primary amides tend to have higher melting points, boiling points, solubility than corresponding carboxylic acids. Secondary and tertiary amides, we can't make a generalization, but they're pretty similar to carboxylic acids. And that's because when we put now a methyl group or ethyl groups coming off of this, you sort of reduce the number of hydrogen bonds. So they're either similar or lower, so slightly lower than carboxylic acids. All right, so that wraps up our discussion of amides. I hope that helps.